we are talking about overcoming restrictions of GPU graphical pipeline with Mesh Shaders. So let's start with parts, part by part. So first, why do we use even the GPU itself? Because, like, why don't we just use CPU only? Because the GPU has more parallelism to be able to, for example, do matrix multiplication or algebra calculations, which are needed for games, for example. We do, you know, that we have matrices for rotation, scaling, and so on. And we can do them in parallel. So GPU is better for that, while CPU is better for executing things in order. So, what is the GPU graphics APIs? First, what is an API, actually? API is an abstraction or a specification of how we can control the GPU and tell it what to do for us. It's not about we cannot say it's a library. For example, OpenGL is a specification like C++ itself. It tells us you should have a function that does this thing and takes these parameters. But it might be available in many languages, such as OpenGL has in Java or C++. Anyway, I used Direct 3D 12 because I need it for the Mesh Shaders, which we'll talk about later. It's a new feature, and that's why I needed the latest one. Vulkan has it also, but it's kind of not beginner friendly. It has more concepts. Like resource description is a little bit harder, so I moved to Direct 3D. But actually, Direct 3D has documentation is worse, but it was worth it because also in the industry it's more used because Microsoft pays companies to use it in their engines. So usually I find games all in Direct 3D 12 and Vulkan or just Direct 3D 12. Yeah, so Metal is for Apple and so on, and I will have problems because I don't have a MacBook. Yeah, OpenGL is all for this. There are others which are not common, that's why it's not worth it to use them and suffer with documentation and so on. So let's talk about the graphics pipeline. So on the right, I couldn't find the horizontal image for the pipeline. So we have first the input assembler. So we have vertices, let's say a triangle. We have 3 vertices, points. And we have indices, or we might not have indices, because for example, if we are drawing a square, we can have only 4 indices, and just also 4 vertices, and we change the order of how we draw them. We can save memory by indices. So in the input assembly, we take the indices and the vertices, if indices exist, and we give them to the vertex shader. Vertex shader does transformations, for example, on vertices such as rotation or transformation, so scaling or so on. So then we go to the tessellation stages. The tessellation stages are like you can, for example, have a face of a person, and the surface will be more detailed. Like for example, triangles will become smaller triangles. And it will give us better details and so on. It's also programmable. For example, in Grand Theft Auto, if you can drive a car and you find the building is getting more detailed as you come closer to it. This is like tessellation shader doing the work. Let's put a geometry stage shader. Yeah. This takes the vertices and assembles them in the way we defined it previously in our code. For example, if I define the triangles or lines or so on. Of course, it can be lines before. I kept saying triangles because it's easier to understand and the most common one usually. Then we have stream output stage. It takes the results of everything we have and puts them in the memory of the GPU. So we can, so it can be accessed by other stages and so on. Then we have rasterizer. Rasterizer takes the camera. We have a far plane and close plane. it's like a theater, and then we take only what's between them. For example, if things are too far, we in the depth buffer, we just discard them. If things are too close, like under the camera, it's like if you are too close to the camera, you become under it, and so on. This is behind the near plane, so we take only what's between the two planes, and it gives us the pixels. In pixel shader, the final value of the pixel is determined, like blue, red, yellow, and so on. And the output merger takes all these and gives them to our screen so we can see what's happening. So on the left we have, in Direct 3D we have root signature. In Vulkan there's similar concept. Root signature tells the shader how to use the data we upload to the GPU. So it does not know how, GPU does not know how to use the data. And inside the root signature we have descriptors, descriptor tables, and we have ranges. Ranges tells the GPU in this range, for example, you can read, or in this range, the resource I'm using is there. And in ranges, we have descriptor heaps related to ranges, and heaps we store descriptors. What are descriptors or views? They are about telling the GPU how to use our data. So if we want to, the description itself might not fit in the root signature. So we might put it in a heap called the descriptor heap. And the resource heap is where the actual data is. And also we might even not use a resource heap and put also the data in the root signature. Root signature has a limit of 246 kilobytes. So it depends what we are uploading to the GPU, and of course the bigger the data, the more in directions, like it will go to the descriptor range, then to the heap, then to the resource heap. So it will be 3. So cache misses will be more probable. Yeah. So how do we in general improve the performance of the GPU? So we have ways, and each way has a cost. Simplifying meshes, like making the things we have less detailed, but that will be bad for industry, for example, drawing, for animations, like movies and so on, or for games, like people like higher resolution usually, if they don't focus on gameplay, and or we can just optimize the work done in the stages. But the problem is we can eliminate things which won't be drawn. We can make smarter algorithms or so on. But the problem is in the stages, sometimes there are some data we cannot access during the stages. Or we cannot program, like for example, in geometry shader, I only have access to the triangle itself. I don't have access to the 3 vertices anymore. I cannot rotate or so on. So in every stage, I have specific things I can do. I cannot do any, and the hardware also does not, for example, allow me to access some certain stuff. So we are limited to what we can do, and also you cannot populate that to all users. Like if you do some complex things, and you have the problem of distributing it among users or so on. Everyone has to come up with their ideas. So who can? The better is that the graphics company, like NVIDIA, can do certain things, and that's what actually happened in 2019 with the mesh shaders. So mesh shaders are basically provide us with a new pipeline called mesh pipeline. We have first the task shader, which distributes work among mesh shaders, and then the meshes are generated. Let's say this rabbit is a mesh, and then we can program each thread to do what we want. For example, every piece here colored is a thread is responsible for, and they will collaborate as the user programs them. And then we have the pixel shader in the end. Much simpler and faster, and we can get more benefit from the hardware of the GPU. Note that it's in RTX graphics cards only, because the previous ones did not allow us to do so. Also, we have a problem of small triangles. Small triangles consume too much memory because the size of a primitive is limited. So, for example, Here, this is one triangle on the left. One pixel is also one triangle. On the right, we have two triangles, but they consume two primitives. So the GPU does things twice here. So that's a problem. And for example, it might be 4x4, 8x8, depending on the format of texture we are using. So I did two experiments. First, anyway, I took a triangle in all cases and scaled it lower, and made it such that it has one pixel in it, or two, or until 32. First, I kept the number of triangles 5,000, and tried in A, case A, normal shaders, in B, traditional pipeline, and in B, mesh shader pipeline. So my graphics card is RTX 3060 mobile, and I got the following performance. You can notice 67 and 944. Also, for example, we can see this, and we can see even lower latency and lower watts, and much better frames per second. Second experiment is about making the total number of pixels on the screen is the same. Like I always draw 4,800 pixels, but I changed the way I distribute them along the triangles. But of course, triangles are equal sizes. So also to study the effect of small triangles. You see, it's very bad. Small triangles are very bad because we went from 1,814 until 109 in the traditional pipeline on A. But in B, the effect was much less on the mesh shader because they were collaborating. It only went from 1,175 till 960. And the scale factor, by the way, you can put that in the code, in the main function in the repository. So just, you have the benchmarks again, FPS, and render latency, GPU power also is less. And this is the picture of how I generated the 4,800 triangles of 1 pixel. Of course, generation happens once at the start of the program. And that's how we improved the case of small triangles, and we can improve the rendering pipeline. Mesh shaders are not focused on fixing small triangles, but they fix this problem because they fix a bigger problem, which is the performance itself and distributing work better. Yeah, that's all.